Hey there, welcome to another video. So in this video, we're going to talk a bit more about how to use the sum and difference formulas for our common trig functions. So I'm going to lead you through a few examples that are really common. They get asked like all the time, so I'm going to teach you how to go through those. We'll talk about some much more difficult examples that involve some inverses, and then I'm going to prove something for you that now we can with these formulas that I've been stating for a while, that sine and cosine are phase shifts of one another. We've seen it graphically, we just haven't ever proved it. So I'm going to go ahead and lead you through that. So let's get started. Let's talk about a very common situation where you're given sine of some angle that you don't know and cosine of another angle that you don't know that equals something, but then they ask you for a whole bunch of stuff like, hey, find sine of alpha plus beta when you have no idea what alpha and beta are, or cosine alpha plus beta, tangent of alpha minus beta, or any kind of manipulation of that, sine of alpha minus beta. So I'm just going to lead you through three of them. So here's how to get started on this problem. If you don't know all of your trig functions for alpha or for beta, the first thing that you have to do is find them. You see, when we're going through and asking for some of these things like sine of alpha plus beta, well, we're going to need to know sine of alpha and cosine of alpha, sine of beta and cosine of beta, tangent of alpha and tangent of beta, and that's not given to you. So the first thing we're going to do is take some time to actually solve for what cosine of alpha and tangent of alpha are, given what we know about alpha itself. Also, before we get going, I want you to take a look at what I've done to the formulas. I've condensed them. This is fairly common, but it leads to a lot of confusions because students don't know, and they shouldn't really be expected to, what is going on with the signs. So sometimes you'll see formulas condensed like this, where this says sine of alpha plus and minus beta. Here's how to read this. If you read the top sign, sine of alpha plus beta, then follow the top sign here. That would be sine alpha cosine beta plus cosine alpha sine beta. Follow the bottom signs to get the other formula. So sine of alpha minus beta would be sine of alpha cosine beta minus cosine alpha sine beta. Same thing for like cosine alpha plus or minus beta. Cosine alpha plus beta, you'd go cosine alpha cosine beta minus sine alpha sine beta. So you can see that the signs are reversed because that's how the formulas actually work. Cosine alpha minus beta would be cosine alpha cosine beta, but then plus. So you're following the bottom sign and the bottom sign, and that condenses your formula. Same thing for tangent. Plus would give you a plus and a minus. Minus would give you a minus and a plus. So just watch out for that. Sometimes you see those and they're rarely explained very well what's actually going on. So let's get back to our example. The very first thing we want to do is find the other trig functions given what we know. So if sine alpha equals 3/5, and they're telling you something about alpha, it's important to know this. It's important to know the quadrant that your angle's in. Why? Well, because we have a few situations that if we didn't know that, we could get different trig functions. We could get either a positive or a negative cosine, a positive or a negative tangent, and we need to be able to figure that out. So sine alpha is 3/5, and our alpha resides in 0 to pi over 2. Think about this part first. So think about what quadrant that's in. If alpha is from 0 to pi over 2, we know that we're in quadrant number 1. We also know something about sine. Sine of alpha equals 3/5 says that sine relates a y to an r. This idea of opposite over hypotenuse, or a y coordinate value to a radius. Well, if we know that y is 3 and r is 5, and we're in quadrant number 1, then we can go ahead and draw something. In fact, we can draw the angle alpha. So we know that our y value is 3, and our r value is 5 for this particular alpha that is in quadrant 1. So that's a really good representation of that angle. We know, yeah, sine of alpha, whatever that is, in quadrant 1, because that's what they tell us, gives us a height of 3 and r of 5, or a y of 3 would be more specific, and a radius of 5 there. Remember that 3/5 could be a y coordinate on a unit circle itself, but we can also think of this as y over r. We've talked about that pretty much at length. Now, given that, we've got to go ahead and find cosine of alpha and tangent of alpha to be able to find the rest of this stuff. So how do we do that? Well, the only thing that we really need is the x. That's really convenient because by Pythagorean theorem, we know that x squared plus y squared equals r squared, or leg squared plus leg squared equals hypotenuse squared. Now, I mentioned a little while ago, like 2 minutes ago, that it's really important to know the quadrant. Here's why. When you work through the Pythagorean theorem, oftentimes you're taking a square root at the end. So if we take a square root of both sides, we're going to get x equals, oh, don't forget this, plus or minus the square root of 16. You see, that x coordinate, if we hadn't have had quadrant number 1, you could have put a y value of 3 and an r of 5 in this quadrant as well, but the x would have been negative here. The reason why quadrant 1 is so important is so that you know which to pick. That's why I'm always drawing pictures of these things. So we know, hey, quadrant 1 means my y is positive, my r is always going to be positive for us, and my x is going to be positive here because I'm in quadrant 1. So look at the quadrant that it says your angle's in to determine whether to take the positive or the negative square root. In our case, because we know we're quadrant 1, x has to be positive there. I'm going to use positive square root of 16, or just positive 4. Now from there, we can figure out the rest of the things that we need, all the other trig functions. We know what sine of alpha is already, but now we could figure out cosine of alpha. So cosine of alpha is x over r. We know that from a long time ago, but now we can really see it. It's going to be 4/5. Likewise, tangent is y over x. So we know that would be 3/4. Now, when we get down to working through sine of alpha plus beta, when we use our formula, which we can do, when we get to sine of alpha, we'll know it. When we get to cosine alpha, we'll know it. It's 4/5. When we get to tangent alpha, we'll know it. That's 3/4. Without actually ever knowing what that angle is, in fact, which is kind of cool. We're going to do the same exact thing for cosine beta. So cosine beta says, hey, you got 2 square root 5 over 5. But remember, beta is between negative pi over 2 and 0. Negative pi over 2 to 0, remember, this is negative pi over 2. Same thing as 3 pi over 2, but going in an opposite orientation of your angle. So negative or clockwise. So negative pi over 2 to 0 is quadrant number 4. We want to look at that first. So let's write down quadrant 4. We also need to understand what cosine tells us. Cosine tells us x over r. On a unit circle, it's the x coordinate itself. Why? Because it's a unit circle and the radius would be 1. It'd be x over 1. But in general, it's the x distance along the x-axis divided by the radius of your angle, creating that triangle or a point on a circle with a radius of whatever the r is. So for us, we know that's x over r. So if that's true, if that's x over r, then I know I could draw a picture of that. But we're also in quadrant number 4. Now, what happens in quadrant 4? X's are positive and y's are negative. Well, that's possible. With that x, that's 2 square root 5. And with that r, we can get a positive x with an r in quadrant 4. But think about what sine's going to be. Sine's going to have to be a negative value because our y values are all negative in quadrant 4. So we're going to draw this. We're going to do it in the appropriate quadrant. So x is 2 square root 5 and r is 5. So we've drawn the triangle that represents beta with an x of 2 square root 5 and a radius of 5. This would create some big circle with a radius of 5, and this would be not a unit circle, but a 5 circle or something. And that is what cosine of beta represents for us. Now, what do we have to do? In order to find sine and tangent, you got to know what the y is. So we're going to use Pythagorean theorem again. Just be very careful what you're actually solving for. Remember, we're solving for y so that we can find sine of beta and tangent of beta, but look at what y is going to be. Because y is in quadrant number, well, because the beta is in quadrant 4, our y has to be negative. That's what all angles in quadrant 4 are going to do. They're going to have negative y values. We can see that right here. Y was important to know in quadrant 4. Well, because if we didn't know that, you could have written another angle beta with an x of 2 square root 5 and a radius of 5 and had quadrant 1. So we had to limit where we were so we have a definite sine and tangent of that particular angle. So we had to know the quadrant in order to even do that. So let's go ahead and do Pythagorean theorem and we'll see what our y value is. So we have x squared, so we know our x. We also drew a picture of it. So I'm looking here thinking x squared plus y squared equals r squared. And we're going to go ahead and solve for y. Remember that when you square a product, you square both factors in there. So we want to make sure that we square the 2 and we square the square root of 5. 2 squared is 4 and the square root of 5 squared is just 5. So 2 squared 4, square root of 5 squared is just 5. That's going to be 20. So our y squared equals 5. Now, when we take a square root of that, you have a choice to make. But it's not a hard choice because you already know what it's told you. You already know that beta is in quadrant 4. What are all the y values in quadrant 4? What is sine in quadrant 4? Well, that's negative. So if I know that I'm in quadrant 4, my x is positive and my y's are negative. So I'm going to have to choose not the positive square root of 5, but the negative square root of 5. I hope you're seeing why it's really important to know what quadrant your angle resides in, because it determines what your x values are, positive or negative, and what your y values are, positive or negative. That will dictate whether you're going to have a positive or a negative sine, tangent, and cosine. So our y is going to be negative square root 5 because we are in quadrant 4, just like our x's and y's were both positive here because we were in quadrant number 1. So what we're going to do now is we're going to take a look at what we need to find. If we knew cosine of beta, well, we know that already. Let's find sine of beta. And tangent beta. Because we already gave our y value a sine, it will determine the signs of sine and tangent as well. So sine of beta says, hey, here's your beta. We already have that. We now know that y is negative square root 5. Sine takes y over r, so square root 5 over 5. But negative because we're in quadrant 4. Tangent takes y over x. Well, we know that. We know that's negative square root 5, that's our y, over 2 square root 5. It might be tempting to rationalize, but please simplify before you rationalize every time. Square root of 5 and square root of 5, they cancel. You're going to get negative 1/2. So now that we've done that, now that we've found all of our appropriate trig functions, sine, cosine, tangent of alpha, sine, cosine, tangent of beta, now we can find the things they're actually asking us for. So find sine of alpha plus beta, find cosine of alpha plus beta, find tangent of alpha minus beta. So here's what we're going to do. We're going to write out the formula appropriately, using the signs that we know, and then we're going to plug in or evaluate for every trig function we have. We'll have it somewhere up here, which is really nice. That means without actually knowing alpha or beta, we can use the representation of our coordinates, so that ratio, and just substitute that in. So let's be really careful with the formulas and write that out right now. So sine of alpha plus beta. If I remember right, I use this formula up here. It says plus plus, I'm going to have sine alpha cosine beta plus cosine alpha sine beta. So I want to make sure that I've got that right. I'm following my signs. Plus gives us plus. Sine alpha cosine beta, I got that. Plus cosine alpha sine beta, I've got that too. Now, because we've already done the work ahead of time, all we have to do is find these things. So sine alpha, I know that, that's 3/5. Cosine beta, I know that one, that's 2 square root 5 over 5. Three-fifths, 2 square root 5 over 5, plus, I got my plus. Now, cosine alpha and sine beta. Cosine alpha is 4/5, and sine beta is negative square root 5 over 5. So I'm just substituting that in there. If we do just a bit of simplification, we notice that we have a common denominator of 25. So that's going to be 6 square root 5 minus 4 square root 5 all over 25. And because we have that common radical, we can just subtract them. So 2 square root 5 over 25. That's about it. That's exactly what sine of alpha plus beta will give for you. So why these examples are fairly important is they really make you practice using formulas correctly, but they also make sure you understand the interplay between taking a square root with a positive and negative, like a plus and minus, and knowing what quadrant you're in. It's very important when we get to things like trigonometric substitution, things like that, to know where we are when we're drawing triangles and doing substitutions. You'll get there. In calculus 2, it's important to understand the trigonometry behind it. So let's move on to cosine alpha plus beta. We're still going to use the formula. You should honestly try it right now. See if you can get the appropriate signs that come out of that formula. See if you can make our substitutions and simplify all the way down. Of course, I'm going to do that right now. But cosine alpha plus beta says we're going to take cosine alpha, cosine beta. Our signs are going to be reversed though. So cosine alpha, cosine beta, a plus is going to yield a minus between these two products here. So cosine alpha, cosine beta minus sine alpha, sine beta. Now we've just got to find those things. So I'm double checking. I've got my plus and my minus. Cosine alpha, cosine beta, sine alpha, sine beta. That's fantastic. Cosine alpha is 4/5. Cosine beta is 2 square root 5 over 5. Make sure I put my minus there. Sine alpha, well, sine alpha is 3/5. So notice, even without knowing what alpha is, we're just doing a substitution. We already know what sine of alpha is. Well, that's what that's asking for. We know that's equal to 3/5. So we can substitute that in. That's exactly what we're doing here, is just finding what our expression is equal to and substituting it for a formula. So sine alpha is 3/5 and sine beta is negative square root 5 over 5. With a little bit of simplification, hopefully we can see we get 8 square root 5 over 25 plus 3 square root 5 over 25. That common denominator lets us make one fraction. We end up getting 11 square root 5 over 25. Let's do the last one. So tangent of alpha minus beta. Of course, I'm leaving out the sine alpha minus beta, cosine alpha minus beta, but I'm hoping that you can see it's the same idea. I just wanted to give you all three trig functions, common trig functions with at least one iteration of these formulas. So tangent of alpha minus beta. Again, we're going to look at our formula. Usually I let students have that because it's difficult to memorize every formula you're going to get in trigonometry. I mean, it's kind of crazy. So tangent of alpha minus beta, we got to follow the sign down. So tangent of alpha minus beta says minus is on the bottom. We're going to use the bottom signs here. So tangent alpha minus tangent beta, but 1 plus tangent alpha tangent beta. In my opinion, it's a lot easier to do all this work right up front, so you're not really having to go backtrack and find them. But that's just my opinion. You can really do this any way that you want. You can write these all out and find them individually if you'd like. But it's just kind of nice to get this all figured out and just go on a roll and finish them all at once. That's how I like to do it. So let's take a look at these things. All we need to know is what tangent of alpha is. We've already found that. That's 3/4. Tangent beta, we've already found that. It's -1/2. So we're just going to write those down. Just keep in mind it's super easy to make sign errors. So like tangent alpha, that is 3/4, but you're going to subtract a negative. Usually we show those things in parentheses because parentheses maintain operation and they maintain sign. So we know we're subtracting a negative. We're going to end up adding 1/2 over 1 plus these two fractions get repeated. That's tangent alpha and tangent beta. No, don't cancel. I know you want to. Sometimes you just want to cancel them out. But if we could do that, we would have made that formula a lot easier from the beginning. We cannot cancel that out. So 3/4 plus 1/2 over 1 plus 3/4 times 1/2. Go slowly to not make some mistakes here. So 3/4 plus 1/2, haven't done that yet. And then 1 plus -3/8, because we multiply numerators and denominators, means 1 minus 3/8. So let's see. This is going to give us 3/4 plus 2/4 is 5/4. Eight eighths or 1 minus 3/8 is 5/8. And however you want to simplify that, you can. You can multiply it by an LCD if you'd like. Multiply by the reciprocal, which is what I'm going to do. We end up getting just 2. So I hope that makes sense. I hope especially you're seeing the condensed version of our formulas and be able to understand the signs there. Also, hopefully you get one of the most important things is figuring out where your angle is, quadrant 1, 2, 3, or 4, because that determines what you can do with X and with Y as far as your signs go. Your R is almost always positive. There are some cases, like in polar coordinates, where we have a negative R and we'll be reflecting that about the origin. But I just want to point that out that most of the time our R is going to be positive. So I'm going to do one more very similar to this because it has a very awkward quadrant. Then we're going to start exploring a couple different ideas. Let's get started on another one. So we've got kind of the same idea, but a very awkward quadrant. So at least an awkward quadrant representation, and a very awkward thing in an okay quadrant. So number one thing we want to do, if we're asked to find a variety of problems that involve different trig functions we don't know, and we're not given an angle, we're just given a ratio that trig function of angle equals, find the other trig functions first. So you're going to be dealing with a lot of this stuff. Let's find cosine and tangent. Let's find sine and cosine of those given angles alpha and beta in the appropriate quadrant. So first thing, find the quadrant. So let's take a look at what -3π/2 to -π actually means. Negative angles sweep out clockwise. So if this quadrant is -3π/2, that's -π/2, -π, -3π/2, 2 π. So -π/2, -π, -3π/2. -3π/2 to -π is actually quadrant 2. So we're in quadrant 2. Now think about what quadrant 2 does. Quadrant 2 has positive y values and negative x values. So when we get to the Pythagorean theorem, we're going to be making sure that when we take a square root, we're taking the negative for our x. So we're going to sign this. So we know that sine alpha is y over r. And that means that we can find our x value. So we're going to draw a picture of this. If our y value is 5, positive 5, and our r is 13, remember, we could do positive 5 and 13 this way, or positive 5 and 13 this way, but quadrant 2 makes us so we do this one and not that one. So positive 5 and 13. Let's go ahead and do Pythagorean theorem. Let's figure out what that x is, because that's going to yield cosine of alpha and tangent of alpha for us. So x squared plus 5 squared equals 13 squared. Eventually, we're going to get down to x equals plus or minus the square root of 144. This is why it was so important to understand the quadrant, because in quadrant 2, our x's are negative. Yes, we have two choices, but only one of them is the right choice. Only one of them will satisfy being in quadrant 2, and that's where our angle alpha resides. So we know that we've got to take the negative square root of 144, or just negative 12. X's are negative in quadrant 2. That one thought of like what your variable is doing, what your x's and what your y's are doing in each quadrant, really help you decide which one is the appropriate choice. So quadrant 2, x's have to be negative. I'm going to take negative 12. Now that we have that, we can really easily find cosine of alpha and tangent of alpha. So cosine alpha takes x over r, which, since we have our triangle drawn, that's really nice. So x over r, we got that. Tangent of alpha takes y over x. Oftentimes you'll see people do this also. If your x is negative, 5 divided by negative 12 is the same thing as negative 5 over 12. I should use that right up there. But we oftentimes don't like to see negatives on denominators. So y over x, if your x is negative, you can easily move that negative to the front of your fraction or even the numerator. So negative 5/12 is perfectly appropriate. Now we'd be able to fill out a lot of these things right here, like for tangent and for cosine of alpha. Let's go ahead and find sine and cosine of beta. So that quadrant's not that bad. So that quadrant says that your beta is somewhere between pi over 2 and pi. So where is pi over 2 to pi? Pi over 2 is positive, first off, so counterclockwise. Pi over 2 to pi. It's saying beta is somewhere between pi over 2 and pi. Well, that's in quadrant number 2. Again, some thoughts start floating through our mind. What happens in quadrant 2? Y's are positive, x's are negative in quadrant 2. Y is positive, x is negative for this piece of the puzzle. So when we do this, we're going to have to keep that in mind when we start drawing this picture of our angle. So if tangent beta is negative square root of 3, remember what tangent does. Tangent takes y over x. But then, wait a minute. What's our x? Well, right now, if you wrote the fraction, you're probably thinking 1. Y would be negative square root of 3 and x would be 1. But wait, this is really important. I hope you catch it. If you actually do that, if you go to y is negative and x is positive, you're in quadrant 4. This was the main deal with tangent. Tangent is negative in both quadrants 2 and quadrant 4. Well, if we're residing in quadrant 2, it's not okay to have a negative y. Because in quadrant 2, y is positive. It's not okay to have a positive x, because in quadrant 2, x is negative. So when this happens with tangent, assign the negative where it needs to go. So what I mean by that is, if you know you're in quadrant 2, your y's got to be positive and your x has to be negative. Fractions don't know the difference for a negative numerator or a negative denominator. What that means is that we can think about this as negative square root 3 over 1 or positive square root 3 over negative 1. That's the one that fits quadrant 2. So you really might have to think about where this angle is and what manipulation of your sign makes it happen. For us, we know that negative y does not work for quadrant 2. So I'm going to think about this as positive square root 3 over negative x. Does that still make the same ratio? Well, yeah, it's still negative square root 3, but it fits our quadrant better. So y is square root 3. And x is negative 1. That puts us squarely into quadrant number 2. Now we can find r, and that's going to allow us to find sine and cosine of beta. So when we take negative 1 squared, we're going to get 1. Square root of 3 squared gives us 3. And when we take a square root, we're going to get r equals plus or minus the square root of 4. Which one do we take? We want to keep r positive because it will keep us in the same quadrant. So your x's and your y's really put you in the correct quadrant. All right, so that r, we don't really ever take the negative, because if we did take negative r, what that would do is that would swing us all the way back into quadrant 4, which is what we were trying to get away from in the first place. So in general, you really just keep the positive when you're dealing with this type of trigonometry. So r is 2. And that really does bear out for sine and cosine when you look at what it should be for quadrant 2. In quadrant 2, sine should be positive and cosine should be negative. Tangent should also be negative, and we see that. But if we had a different r, we would be switching one of those or two of those. So sine beta says take your y over your r. That's square root 3 over 2. Cosine beta says take your x over your r. That's negative 1/2. Man, this one, actually from the beginning, we probably could have figured out what the angle even is, because tangent beta equals negative square root 3. That's actually on our table. Sine beta equals square root 3 over 2. Notice how that's in quadrant 2. That's positive. Cosine beta equals negative 1/2. That's in quadrant 2. That's negative. That makes sense. We could figure out that beta. Maybe do that. But for us, we don't actually have to. We have everything lined out to be able to fill these out really, really nicely. So if we were trying to find sine of alpha plus beta, and we know that it's sine alpha cosine beta plus cosine alpha sine beta, we know sine alpha, we know cosine beta, we know cosine alpha, we know sine beta. We're just going to fill that out. So sine alpha is 5/13, cosine beta is negative 1/2. Cosine alpha, that's negative 12/13. Sine beta is square root 3 over 2. We're going to simplify a little bit. We're noticing that we get a common denominator. This happens very frequently. That's going to be, well, let's see, 13 times 2 is 26. So negative 5 over 26 minus 12 square root 3 over 26. There's not much we can really do to simplify that. It just stays as ugly as that is. Unless you can factor something and simplify it, you're going to leave that. Let's do the same thing down here. So cosine alpha plus beta, we already have the formula lined out. Cosine alpha is negative 12/13. Cosine beta is negative 1/2. Minus, we got to get our sign right. Alpha is 5/13, and sine beta is square root 3 over 2. So I'm getting a positive 12 over 26 minus 5 square root 3 over 26. It might be tempting to simplify this, but then we lose our common denominator. And it's nice to see this as one fraction. Not super necessary, but sometimes kind of nice. All right, tangent, last one. So we took care of tangent. Tangent alpha is negative 5/12. Tangent beta is negative square root 3. All right, so we have negative 5/12 plus square root 3 once we simplify. And we have 1 plus negative 5/12 times negative square root 3. That's positive 5 square root 3 over 12. Now what to do here is pretty ugly. This is one of those cases where it might be nice just to multiply everything by the LCD. So let's multiply both the numerator and distribute, and denominator and distribute by that 12. So let's go ahead and do that now. So we have 12, hey, that cancels, that's negative 5. We have 12, that's 12 square root 3. 12 times 1 is 12. 12 cancels here, and we get 5 square root of 3. As much as we want to simplify that, you might be able to rationalize the denominator, but that's about it. Nothing there actually cancels out. So I'm going to leave it there. If you want to rationalize, you'd multiply by the conjugate of the denominator and distribute that. All right, so easier one involving inverses and then tougher one involving inverses. So what to do and what not to do when you're dealing with sine of stuff that's added together with inverses. Firstly, could you distribute sine into here? No. Sine is an operator. It's not a value. So you can't just distribute this and get sine of this plus sine of that. It doesn't work that way. That's why these formulas exist. Because if you could do that, you could do sine of alpha plus beta would be sine of alpha plus sine of beta. Well, that's not true. Sine of alpha plus beta is all of this crap right here. So it's not like we can just say, I'm going to distribute. It's non-distributable. That's why the formulas exist. So we have to really work on this before we can even touch that. Now, does it make sense? Does this actually make sense? What do inverses give you? Sine inverse of 1/2 says sine of what angle gives you a relationship of 1/2 for y over r. So this is talking about an angle. So is that one. So inverses give you out angles. Remember that? Sine of angles give you out points or relationships of points. And inverses, sine inverse of points give you out angles. So sine of stuff that is angles actually does make sense. So what do? Firstly, if you can figure these out explicitly, do it. It'll save yourself a lot of time. And we can do that here. You see, sine inverse of 1/2 must equal some sort of an angle. And that only works if sine of that angle equals 1/2. So sine inverse of 1/2 is an angle. Inverses give you out angles. But this is true if and only if sine of alpha gives you 1/2. So where does sine of alpha equal 1/2? What angle gives you at a y coordinate on a unit circle of 1/2? Remember, we're back to a unit circle right now. That's the only time inverses work, is on a unit circle, and they only work on the restricted domain. For sine inverse, I hope you remember, sine inverse works from negative pi over 2 to pi over 2. So when we're asking this question, sine inverse of 1/2 equals alpha, it's what angle gives you a y coordinate of 1/2, because that's sine, but only from negative pi over 2 to pi over 2. So sine alpha equals 1/2. What angle gives you out a y coordinate of 1/2, but only from negative pi over 2 to pi over 2? Well, let's see. That's got to be pi over 6. Now remember what we did. We just called sine inverse of 1/2 alpha. We just found alpha. Alpha is pi over 6. So what that means is this piece is now alpha. That's going to be pi over 6. Let's find cosine inverse of 0. Remember, these don't have to be the same angle, so we're going to call it something different, like beta, conveniently. Cosine inverse of 0 equals beta if and only if cosine of beta equals 0. But remember about cosine. Cosine inverse only works on the unit circle, and it only works from 0 to pi. So we're asking what angle gives you an x coordinate of 0 on a unit circle, but only between 0 and pi. Well, that's got to be pi over 2. Pi over 2 has an x coordinate of 0. That's not a 2. So we asked, hey, sine inverse, negative pi over 2 to pi over 2, what angle gives you a y coordinate of 1/2? That's pi over 6. And we said cosine inverse, that's 0 to pi. What angle gives you an x coordinate of 0? That's going to be an angle of pi over 2. So we have this. We already called cosine inverse of 0 beta. Beta, we just found that. So cosine inverse of 0 is pi over 2. So we can change our problem. Now, instead of just having sine of something that we don't know, we now know those angles. Now, could you add those together? You could. And sometimes it's worth doing because if it's still on your unit circle, that's absolutely just fine. So pi over 6 plus pi over 2, let's see, that's 3 pi over 6. That's going to be 4 pi over 6 or 2 pi over 3. So you can totally do that. Do you have to? No, you don't. And sometimes it doesn't work very well that you have two different angles that add together and it's still in a unit circle. Sometimes that doesn't happen. And so oftentimes we'll just use the formula right from here. I'm going to because I want you to practice, but keep in mind, you could add this, and if it's still in the unit circle, that's okay to do. So we've got our formula all worked out. We have sine of the first, cosine of the second, plus cosine first, sine of second. That's what our formula says to do. We have the signs the same for sine. Now we're going to use our unit circle. So sine of pi over 6, that's going to be 1/2. Cosine of pi over 2, we already know that. That's going to be 0. Cosine of pi over 6, that's square root 3 over 2. Sine of pi over 2 is 1. So 1/2 times 0 is 0, plus square root 3 over 2 times 1 is just square root 3 over 2. Now, what if we had added them? This adds together as 4 pi over 6, or 2 pi over 3. And sure enough, sine of 2 pi over 3 is exactly square root 3 over 2. So it does work if you add them together, provided that is still in a unit circle. If it's not, then this is the way to go. So there's two options. Either one is really just fine. That can save you some work sometimes though. So I hope that makes sense. What I'm going to do now is come back with another one where these things are not just easy to find, where this is not on your unit circle. I'll show you how to walk through that. All right, so last one before a couple proofs of what I said I'm going to do and teach you that sine and cosine, not just graphically, but literally are phase shifts of one another. So I'm going to show you that in just a little bit, some proofs, and some interesting kind of formulas, identities that we can use from here on out. So it looks really similar to the last type of example, and at first glance, we really want to do it the same way. We want to say, hey, that's an angle, that's great, those add up, cosine of that, easy peasy. But that's not a unit circle, and neither is that one. So what we can't do, man, don't distribute that. It's not going to help you anyway. But we have to find some way to represent that and that as an angle. So here's the thought process. If I can represent this as an angle, then tangent of that angle equals 4/3. That's something I can draw. That's something I can find sine and cosine for that particular angle. Same thing here. I can write that as an angle. Cosine of an angle equals 5/13. That's something else I can draw. That's something I can find sine and cosine for. Well, if I do that, then I can take cosine of alpha plus beta, whatever those angles are, and use a formula. And using my pictures, I can plug in some fractions that represent the ratios given sine of alpha, sine of beta, cosine alpha, cosine beta. So let's set this up as an angle first. So starting from the beginning, hey, those are inverses. Let's call them an angle. If they're not on the unit circle, we're going to have to draw a picture of it. So tangent inverse of 4/3 equals alpha. Inverses give you out angles. But this is only true if tangent alpha equals 4/3. Now we're about to draw a picture, but remember this. Tangent inverse only works from negative pi over 2 to pi over 2. Why? Well, because there's two places on a unit circle where tangent's positive, and two places on a unit circle where tangent's negative. But if I restrict it from negative pi over 2 to pi over 2, there's only one quadrant where tangent's positive and one quadrant where tangent's negative. So if tangent's positive from negative pi over 2 to pi over 2, it has to be quadrant 1 where that's happening, not quadrant 3. That's off limits for tangent inverse. So this angle must be in quadrant 1. I need you to see that. You see that because we're tan inverse, we're somewhere from here to here. Because tangent's positive, that is in quadrant 1. That's a positive y and a positive x. That's only quadrant 1. I can't assume it's a negative x and a negative y, which would still give us positive 4/3, because we can't be in quadrant 3 for tangent inverse. So this is y over x, saying we're going to have y of 4, x of 3. And we can certainly find our r for that. We almost exclusively keep r positive, so we're going to take positive 5 here. And we're going to keep on going. We're going to find cosine of alpha and sine of alpha. Why? Why in the world would you do that? Well, really get this. We just called this equal to alpha. So this whole thing right here is alpha. That there is going to be beta in just a minute, but we're going to have cosine alpha plus beta. We've got a formula that shows us that. So if we have cosine alpha plus beta, we can write this as cosine alpha cosine beta minus sine alpha sine beta. If we can just find sine and cosine of alpha, we can fill out that formula when we get there. So let's go ahead and find sine and cosine of alpha. Sine takes y over r, so that's 4/5. So sine alpha is 4/5. Cosine alpha takes x over r, so 3/5. And we're ready for that one. So cosine inverse of 5/13. Let's call that beta. So inverses give you out angles. But that's only true if cosine beta equals 5/13. Now, we all know about cosine. Cosine beta, cosine alpha equals 5/13, and that's x over r. So x is 5, and r is 13. But think about where cosine inverse works. Cosine inverse only works from 0 to pi. You see, there's 2 quadrants where cosine's positive and 2 quadrants where cosine's negative. And so if we left this alone, we would be able to draw 2 different pictures here. We can't let that happen. So cosine here is positive. The only positive quadrants from 0 to pi is quadrant 1. So this is in quadrant 1. That's a positive x and a positive r in quadrant 1. So let's draw that. Obviously not to scale. All that really matters, and I hope that you're seeing it, that understanding the quadrant is very important for what we're doing here. We have to have the right angle in the right quadrant so that we can find the right signs for the rest of our trig functions, like positive or negative for the y, positive or negative for the x, always positive really for the r. So we said, hey, cosine inverse works from 0 to pi. Because it's positive, the only quadrant from 0 to pi where cosine's positive is quadrant 1. We have to draw this in quadrant 1, and we have done that. You can't make it quadrant 4 because cosine inverse doesn't work in quadrant 4. That would have a positive x and a positive 13, positive r, but it wouldn't be appropriate because that cosine inverse doesn't work there. So now we're going to go ahead and find y. If we take plus or minus the square root of 144, we got to understand that this is in quadrant 1 and the y is going to be positive in quadrant 1. So we can see it. Sine is also positive in quadrant 1, so we know that we need to take the positive there. That's positive 12. Now we already have cosine of beta, but we certainly want to find sine of beta. Which in our case is 12/13. Question, why aren't we finding tangent of alpha and beta? Well, we have tangent of alpha already. Why don't we care about tangent beta? Look at your trig function. Our trig function is cosine. Cosine of alpha, we have a picture for alpha, and beta, we have a picture for beta. The formula for cosine of alpha plus beta has absolutely nothing to do with tangent, so we don't need it. It'll not come into play. Now, if that had been tangent, then yeah, for sure, we would have needed that, but we don't here. So all we've done, really just a little recap, is that was an angle, let's call it alpha, find a picture, and find sine and cosine, because you're gonna need it later. Call that an angle, draw a picture of it, find sine and cosine, because you're gonna need it later for that formula. Now, because this is alpha and that's beta, let's use cosine of alpha plus beta to write our formula out. So I have cosine alpha plus beta, cosine alpha, cosine beta, minus sine alpha, sine beta, and we have all of this stuff right here. So cosine alpha, that's 3/5. Cosine beta, that's 5/13. Minus sine alpha, that's 4/5. Sine beta, that's 12/13. We can do a little bit of simplification, but it might not be great to do that, because if we simplify this, we can't simplify that, and we lose our common denominator. So that looks like that is 65 as a common denominator, so 15 minus 48 over 65. All in all, that's negative 33 over 65. It's kind of ugly, but you can't simplify that. And that's really all there is to it. Kind of a weird little example that says, hey, cosine of this angle, what's that even mean? The x-coordinate of something on a unit circle with this angle that we don't even know, made up of two inverse functions added together, would be an x-coordinate of negative 33/65 on a unit circle. So hopefully you found it quite interesting. At least it's really good practice. So what we're going to do now is I'm going to show you those proofs of how sine and cosine are really actually phase shifts. Also, these formulas are great for identities moving forward. Okay, so last little bit. These are some very standard identities that you get in any textbook. Those are not. Those ones I'm going to show you because this proves the phase shift idea, but you're really going to want to make sure you understand these two. They come up quite often. They're a way that you can change from cosine to sine or sine to cosine. Same with those, you can do it. So I'm going to prove them. I'm going to show exactly what this is. It's really just using our sum and difference formulas for cosine and sine, and then sine and cosine again. So let's go through, let's really see what's going on here. So if I have cosine of pi over 2 minus theta, you can really think about that as a difference of two angles inside cosine. Let's use the difference formula for cosine. So cosine pi over 2 cosine theta, different sign, so plus sine pi over 2 sine theta. That's what our formula says. Now, cosine of pi over 2 is 0. So this whole thing, 0, cancels out. Cosine of pi over 2 is 0. What about sine of pi over 2? Sine of pi over 2 is 1. So wait a minute. If we use the difference formula for cosine, then cosine of pi over 2 minus theta is actually equal to sine. We just proved it, and that's a very nice identity to use. Honestly, we can prove this one directly from here. If we took this and reversed our terms, factored out a negative, and used the fact that cosine is even, to say opposite inputs give you equal outputs, it doesn't matter whether that's a negative or not, that's still going to give you out sine. Now I'm going to prove it with the difference formula again. Maybe you can do it on your own, but that's also going to equal sine theta. This is going to equal, well, let's see. Let's figure out our formula. Sine of pi over 2 minus pi. Minus theta. All right, so sine of pi over 2 cosine theta, so sine of the first, cosine of the second, keep the same sign for this difference formula for sine. then cosine of the first, sine of the second, we have that down. Sine of pi over 2 is 1, we know that. Cosine of pi over 2 is 0. That takes care of that whole term there. That means that we're going to get just cosine of theta. So, if we ever have pi over 2 minus an angle, sine of pi over 2 minus that angle, or if you can write it that way, sine of pi over 2 minus that angle is going to equal cosine of whatever your theta is. Same thing here, cosine of pi over 2 minus theta is going to equal sine of whatever that theta is every time. Now, this is going to prove our phase shifts. So sine of theta plus pi over 2, try it on your own. All right, I've gone ahead and written those out. So sine of theta cosine pi over 2 plus cosine theta sine of pi over 2. Cosine pi over 2 is 0. This whole thing is gone. Sine of pi over 2 is 1, giving us cosine theta. Something very similar happens here. Cosine pi over 2 is 0. This is gone. Plus sine of pi over 2 is 1, leaving us sine of theta. Now, appreciate this. Appreciate the graph with what that says. You just need to remember your transformations. Do you remember that whenever you add or subtract something inside the parentheses next to your input, inside input means you're moving left or right. So you're affecting the input. Now, how does it affect it? If we add to that input, it actually shifts our graph left. If we subtract from that input, it actually shifts our graph right. So here's what this says. Cosine is actually just the sine function shifted to the left pi over 2. The cosine here is in purple. If you take sine and shift it left pi over 2, this whole thing goes boop, you actually get cosine. This is sine and that's cosine. Now take a look at this one. It says cosine theta minus pi over 2 equals sine theta. Here's what this says. Sine theta is if you take cosine and shift it right pi over 2. If you take cosine, shift it right pi over 2, you're going to get sine. Here's cosine, it's purple. If you shift it right pi over 2, you're going to get cosine. This is like algebraic proof that cosine and sine are just phase shifts of one another. They give you the same graph, but they're off by pi over 2. So you need to take cosine and shift it right to get sine, or likewise take sine and shift it left to get cosine. That should make sense. They're phase shifts of one another, and now we finally got to prove that because we have a couple formulas that let us. So I hope this video has made sense. I hope I've really hammered down on what sine and sum and difference formulas for sine and cosine and tangent are. I hope that you've enjoyed it, and I'll see you for another video.